there was a second derivative test that's used in Calc 1. Now this is the second derivative test for Calc 3. Let's say you have a comma b is a critical point of your function of two input variables. And remember that that was probably discovered by setting f sub x and f sub y equal to 0. Then compute the discriminant. Now that's not technically part of the second derivative test. It just but look, the way that the books tend to word these things, they don't really kind of procedurally talk about what you need to do. I'm just mentioning in gray, yeah, you're going to need to compute the discriminant because the second derivative test, and you'll see in just a moment, talks about the discriminant quite a lot. So here's the thing. If the discriminant evaluated at the critical point gives you the number 0, inconclusive, you get no information. That kind of thing happens in second derivative tests. We've seen things like that before. Now, if the discriminant is negative at the point a comma b, then a comma b is a saddle point of f. If, however, the discriminant at a comma b is positive, then f has a local extremum at ab. Now, the question is, does f have a local min or does f have a local max? Well, if f sub xx at the point a comma b is negative, then f has a local max. If f sub xx is positive at that point, then f has a local min. Now, here again, this looks a little funky, but this goes back to this same idea where in Calc 1, f prime prime less than 0 is what led to a local max. Some comments are in order. Yeah, f sub xx less than 0 sounds similar to f prime prime is less than 0. Okay. Similar comment for f sub xx greater than 0. Now, the text to compute the discriminant is written only in gray because it's not informing the person who's doing a problem that you need to compute the discriminant isn't technically part of the second derivative test. But you'll notice that the discriminant is mentioned 3 times actually otherwise in the second derivative test. So you would need to do it procedurally speaking, so that's why it's just being mentioned. Okay, how would you be able to tell if, really you have to compute it, right? Because how else would you tell that the discriminant is 0 or negative or positive without actually computing the discriminant after all? So let's go ahead and apply this, right? Let's take the earlier example we had, apply the second derivative test. We already computed our partial derivatives. Again, apologize for the typo. This should say 3y squared minus 6y. And we had second partial derivatives, and we got the discriminant, all these things. We already found 4 critical points, and now we're just going to take each of the 4 critical points and run them through the second derivative test. So the point 0, 0, when you compute the discriminant, you get negative 36, and that means, remember, if the discriminant is negative, you get a saddle point. So this function has a saddle point at 0, 0. Take the point 0, 2, compute the discriminant to be positive. So we have a local extremum, right? But what kind of local extremum? Well, when you look at f sub xx, that's why it's been rewritten up here, 6x plus 6. If you evaluate this at the point 0, 2, you get the number 6, which is positive, right? And that second, the second partial derivative being positive, that means that you're going to have a local minimum. Okay, local minimum at the point 0, 2. Look at the point negative 2, 0, discriminant is positive, 36. That positive means local extremum, so what kind? Well, compute f sub xx at negative 2, 0, and you get a negative number, so you have a local maximum at negative 2, 0. Finally, the point negative 2, 2, that's the 4th and final critical point. The discriminant is a negative number, negative 36, so we again have a saddle point. There are 2 saddle points, and a local min and a local max. Right? So that's our summary so far, right? So for this function, 2 saddle points, they're at 0, 0 and at negative 2, 2. There's a local min at 0, 2 and a local max at negative 2, 0. So let's go take a look at a contour map and see all of these features. In fact, what you're going to see is one level set highlighted in black. We'll click on a circle to show all 4 critical points with their labels. We'll change the value of k, which output for the highlighted level set, to verify in fact that 0, 0 and negative 2, 2 are saddle points. We'll change the value of k, the output for the highlighted level set, to verify that there's a local min at 0, 2, and do the same, change the value of k to verify that there's a local max at negative 2, 0. Okay. All right, so here are all those things that I would like to check on. So you actually see a contour map. There are many, many level sets here. And so the many different level sets are shown in red. And then one level set is being redrawn. It's drawn on top of, in fact, in black. And right now we're seeing the level set with corresponding to output 3. All of these points have z value 3. And let's just lower the value of k, and you'll notice that, okay, so the point is that there's a saddle point here and a saddle point here, because if you move from, let's say, this saddle point here, let's turn on these points. Yeah, from this, the saddle point that's in the upper left, if you from there move up, the value of k is increasing when you increase y. Whereas if you move left or right, the value of k is decreasing, right? And then sort of the opposite phenomenon occurs at this saddle point. A movement in the x direction leads to bigger output values, and then at this saddle point, a movement in the y direction leads to smaller z values. Okay, and then let's keep decreasing the z values, and stare over here at these circles. So all these kind of, they're not quite circles, I guess, but these kind of oblong circle-like things, we're seeing z values that are smaller and smaller and smaller until you get to right at that local min. And if we increase z values, or increase the value of k, you can see us honing in on that local max over here as well. Interactive question. Write a short text on how to use the app mentioned to show that -2, 2 is a saddle point. Provide enough detail regarding how the slider for k should be used. Be sure your answer references input, x, y, and output. Help somebody out. Imagine that somebody is struggling to really see the saddle point. Tell them how to use the app. Okay, how do we find global max of f of x, y in a region R? I want you to note that a lot of the ideas that you're about to see here are reminiscent of tasks in Calc 1, right? So you find all the local maxes in the interior of a region, and then compute local maxes on the boundary. This is just like checking endpoints in Calc 1. And then look through the list to see which input gives you the largest output. So step 2 in the list, checking the boundary, is a lot like checking endpoints in Calc 1. As the first question of today, we're talking about finding the global max of x cubed minus 3x for x belonging in the interval -1.5 to 3. So I'm using capital R serving the same purpose, right? So R is a certain subset of the input space. And we had to check what the output was at the two boundary values, at x equals -1.5 and at x equals 3. So we'll see examples of this kind of thing next time, of not only doing local mins and maxes, which was the main focus this time around, but next time you'll see a focus on what do you do if you're given a region and how do you check the boundary.